Today we'll go over an intuitive look at NMOS logic through the ages and power consumption, and even tied into multi-state logic devices. Um, I'm going to start with a 3D MOSFET, looking at all the various parasitic capacitances, because it actually turns out that's the limiting thing that can limit speed and power. Um, so just to keep us all on the same sheet of music. All right. So here is a 3D 3D abstraction of an NMOS transistor. All right. Now let's see if I was lazy today and I was trying to find pictures. Um, and I tried a chat GPT one, and I guess I just deleted it because it was really bad. Okay. It would be great to say, here's a picture, tell me what's wrong with it for an exam question. All right, so here's the schematic. We have the drain, source, and gate. The body's not shown. A lot of times in schematics you don't, um, because it's tied in one location or several locations, and it distracts from the flow of data when you're talking about something. So what we have here, the blue regions are the source and drains, and they're doped, again, in this easy model, they're doped constant, okay? So we start off with abrupt junctions. And then everywhere surrounding it, except on top, is p-type silicon doped to n-type, p-type. All right, here in the yellow is the oxide thickness, right, which generally tends to be a lot thinner than everything else, so I just blew it up over here. So from here to here is T-ox, right? Covered with, in this case, I put like an aluminum gate, but it's, polysilicon or some other advanced material, right? This is the gate to drain overlap or gate to source overlap. And I just blew it up so you could see it better, all right? Now, we're going to see that we'll draw a width and a length. And so from here to here is like the drawn length, but by the time you're done processing, it creeps under the gate. And so there's an effective length. And not only that, when you would also subtract out the depletion widths. And so when they say a technology is 130 nanometers, they're usually talking about the effective length, not the as drawn. Some other things is that here are the contacts that the current comes in and out of. And a quick thing about scaling, right, is that when make a smaller device, you shrink L drawn, and that allows you to shrink W to get the same kind of current. But to keep the uh, as ideal transistor properties um, as constant as can be, well, you end up shrinking the gate ox as well. And if I shrink the width and the length, right, well, still I've got this source and drain region, which is causing a capacitance, right? And a quick aside, right, all this blue area would be N-type, everything around it would be P-type. So we have 1, 2, 3, 4 sidewalls. That's a PN junction. That adds to the capacitance. And then this bottom part, which is another junction, right? So you have XJ, sometimes it's called RJ, and you have width and then depth of drain. Now the thing is what is the minimum width and the minimum depth of drain? Well, you can get the length smaller, but these contacts don't scale as well. They haven't scaled for a long time. So they kind of stay the same. And you need space around it to make sure that everything can be manufactured. So you can shrink RJ to a certain amount, but the width, the minimum width, can be hard to shrink beyond a certain point because the contact and the overlap, the space you need for manufacturability doesn't scale well, and then you need this part here. All right. And so in some ways, the parasitic devices are controlling the speed and actual things. All right. So I'm just picking on this area here. We usually think of as the drain capacitance as something that needs to be charged and discharged. Many times the source, right, is tied to ground, and so the PN junction is shorted, and so there's no capacitance to charge and discharge. Another capacitance that we have to worry about is the overlap, right? Because that provides a feedback path between the gate and the source or the gate and the drain, and that can cause some interesting effects. Um, and then if this were being driven, right, it becomes a load, and you have the width times the length. That gives you the area times the capacitance due to the oxide. All right. So just in summary, right, the drain capacitance can really dominate everything. And we'll find that manipulating that or avoiding charging and discharging it altogether will save us some power later. But we don't normally think of things like this. It's a little too hard to draw. And so we usually have, this is what you see under the microscope and a tool like Magic or Cadence, and you're drawing these pictures. All right. But then when we're talking about things, we even have a simpler way of doing it so that we can have a much easier discussion. Let me get my pad working here. So I'm just going to right, that would be my active region. And then this would be my gate. And what this implies is the blue would be an area that you grew a thin oxide, then you put a polysilicon, etched it, right? And then you did an N implant to turn these N-type, right? But even that is too much to draw. So what we do is a stick diagram, okay? And yeah, I'm drawing it out of sequence, okay? And that's the W. Oops. All right, I'm going to pause while I charge this up. Okay. Just want to make sure everything is working. So this would be a more complex drawing of the MOSFET, and then we have something called a stick diagram. So we went from a 3D to a top-down, 2D, something you would draw, to a stick diagram. Now, just as a quick aside, um, Tiny Tape Out has this thing called SillaWiz, and it has a drawing tool that converts it to a spice file, which actually you can cut and paste and put into LT Spice and run. And it tells you what the layers are of the Skywater 130, right? And then what you draw here, you can have it do an abstraction of a 3D cross section, right? And so, and it has a few exercises that can really, if you just go and do it, you will learn quite a bit. Just, even from a voltage division, making capacitors and things like that. Really, by doing these exercises, you can bring yourself up to speed rapidly. All right, so back to business. So really, we have a source and a drain, and they're kind of interchangeable depending on how they're hooked up, and you have a gate. And you can, the reason why we draw this just as a line is that the length on a digital process is always as small as it can be, right? So I don't need to draw it out, right? Unless, actually, for some of the NMOS things we'll do, the length will be longer, right? But really, we're concerned with the width. And then this overlap, depth of drain, is really, controlled by, the contact and the design rules to make sure that this is manufacturable. All right. So now we'll go back, or we'll start just to talk about NMOS logic. Okay. And yep, there's a lot of physics that goes in here, but really we have something called the threshold voltage. And if the gate to source is a lot bigger than the threshold voltage, you will get a lot of current flow. All right. And if it's below, you will get a very small amount of current. So in this particular example, right, if I have VG, equals VN, and VG with respect to source in this case because it's tied to the body, right? At some point there's the threshold voltage, right? Well, if this is voltage is below threshold, no current will flow, right? And that means there can be no voltage drop across the R. So VD equals VDDD, VDD, okay? And then here, when we increase it to where we're getting the maximum current flow, right, there will be ID times R drop across here, and it can get, depending on the conditions, very close to zero, right? But not exactly zero. And so here we have a low input making a high output, and we have the inverse here, and so we have an inverter. Now, some problems with this is that resistors in an IC process tend to be pretty big. And if you actually go to the SiliWiz, you can draw your own resistors, and you can see. All right, so even though it's a simple device to make, we'd much rather have it in a transistor, which we can control the resistance with voltage and make things smaller. The other issue is ID, and below 3 VT, it's small, but then it goes up. And now we're going to talk about the thing that drives everything, is that power equals ID, and then whatever's falling across the whole stack, right? Which we can just assume to be VDD. Yes. Oh, actually, the current flows through both devices. So even if there's a voltage drop here, current is flowing through everything. Current times voltage is power. All right. So that means, you can have, if you had 1,000 inverters on your chip, right? And the probability of low, right down here, we could say is 1/2. That means 1/2 of these inverters are burning a lot of power. Just um, doesn't matter the clock speed or anything. You are just burning a lot of power, right? And just as a prelude, that's static CMOS will solve that problem. But going through the history, CMOS certainly more advanced than this process, takes more masks, and CMOS was invented a long time ago, but could you make it commercial? And it was also considered very slow for the device dimensions at the time. So just let's continue our history lesson. So now we have the same driver, right? But now we're going to replace this with another NMOS transistor, same threshold voltage, everything. Okay. And we're going to connect it, diode connect it. All right. So I can get the same kind of resistance in a much smaller package. All right. Now, what happens is that this can go rail to rail, right? If no current flows, there can be no voltage drop, and so these get connected. Here, however, in order to charge this node to a value, current does need to flow at some point, and since it's diode connected, nothing flows until you're above VT. So let's call that VDD, but you need a threshold voltage to turn it on. And because the body and the source, are not at the same voltage, the threshold voltage is even higher. All right. And that would be gamma in your SPICE simulation. So actually, you don't get the full VDD. All right. And this is important when one gate drives another gate. So the output high becomes lower and lower as you go through a chain, right? Now, there's a workaround is that I'm just going to call this VDD2, and I can make this much higher than this, right? With the expense of another voltage supply or something, right? And I can get it back up, okay? But both of these suffer from the same ID drain current issue. All right. Now, having that extra voltage supply, we're actually going to use that later. but that was not considered a good solution long term. So they actually made an other MOSFET, and this is almost where CMOS comes from, is that they took an NMOS, right? But they made two of them on the same die, one with a threshold voltage below zero, right? And then one greater than zero. And then they tie it here. And so now you're getting a rail to rail with only, power and ground. Um, and it considered, and it was very fast because both of the NMOSs have electron mobility in the channel, which is higher than PMOS, right? So you can make some very fast chips this way. But again, the same issue with power. All right. So now let's go to CMOS. Now, before we always had a load transistor that we were dropping uh, a potential across to get our output low. What happens here is that with the PMOS, right, that conducts current when the NMOS is off, and the NMOS conducts current when the PMOS is off. And so what happens is you don't really have a load per se. So if I'm charging the output, let's just say there's a load capacitance, right? And I'll call that RP, which is an average of the resistance through the whole charge cycle, right? It just charges it up. But notice the NMOS is taken out of it. And then when the PMOS is off and the NMOS is conducting, you discharge. Now, of course, as it's switching through, they're both on. This is just more the endpoints. What you can see is that this is just like a regular RC circuit. Now there's a lot of the capacitances and a lot of complexities in the RN and the RP, but really, you can understand this with just, first order RC, right? Because you just lump all the C's together. So, you know, when this charges up, right, like 5 tau, then nothing flows. This becomes open. And when you discharge it, nothing flows and this becomes open. So what we get is when you're charged up, you're at VDD. And when you're charged down, you're all the way to ground and you have a transfer curve. All right. So again, let's, right, if V in is high, the PMOS is off, and all the current flows this way, and you discharge the capacitance. And when V in is low, this turns on, this is off, and you charge up. Okay. And again, there's this moment when they're both on, and that's actually where we burn our power. So I'm just going to make a line here, and this is V out versus V in with a slope of 1, right? And so at this point where V out equals V in is the switching threshold. And if we look at the current, it does this. So you start off at a low current, then you burn a lot of current, and then you go back to zero. But you only go through this transition when you switch. So if I'm hanging out at zero or hanging out at VDD, I'm not burning a lot of power. Now, of course, modern devices have leakage, and so there is power. But if I stop the clock, right, I'm not burning any power. If I stop the clock over here, I'm still burning power. All right. Now, where let's take a quick look at the power in CMOS, right? And first of all, we have something called activity factor. And what is the probability that this gate or any gate or all the gates are switching, right? So it's something, between 0 and 1. And if the clock is stopped, it's 0. So the power would be 0 in standby mode. Now then you have like, well, how often are you switching, right? So that would be your clock frequency. All right. Then you have the load capacitance. Now what's that? Well, now you will be happy that I talked about the drain capacitances here, right? There's overlap capacitances, and these gate capacitances would be from the next stage. So let's just go back, right? Here's our PN junction, here our PN junction. Here's our sidewall perimeter, which has 4 sides, has a depletion capacitance, and then the bottom junction has a depletion capacitance. So let's just call this the drain, right? So you have the perimeter times a scale factor for the sidewall capacitance, and then you have this area, depth of drain times W times the bottom junction scaling capacitance, right? And then this is what it would look from the top. What I'm showing is this rotated, where this would be the drain, and then down here would be the source, all right? So that area needs to be charged and discharged, all right? So right now, it looks like it's just, I'm talking about the charge and discharge of a CMOS inverter, right? But there's other gates that I'm about to go into that you really count up the number of drains, and you'll see how that works in a bit. But that C load is every capacitance that gets charged and discharged on the entire chip, right? Sometimes you have a capacitor out here that's really just the equivalent capacitance of a long line that's being a long wire that's being driven across the chip. All right. So now we have improved the power, right? And the way we get power density savings is, well, not everything switches, and then we have, we can stop the clock. And then we also have scaling. And so if we reduce the VD of the power supply, right, you can see that the power can drop dramatically. Now, there's a lot going on with power density here, okay? So that if I scale this length by a half, right, in scaling theory, then on average I can scale the width by a half, right? And then on average, I can scale xj by a half. So if this width is halved and this is halved, okay, now the drain capacitance is coming down. Now, unfortunately, in modern devices, the depth of drain doesn't scale like that, right? So you really end up having to calculate it out to see what will truly happen. But by scaling the voltage, the power is reduction, but then also the power density can stay close to the same. Now, we haven't been able to scale, so then you were able to increase the frequency. right? The devices are smaller and they're faster because the load has gone down. But really, the power density is kind of hit the limit. And so now you try to do things in parallel. All right. So now we have it's pretty good. We're reducing the power, but we do need a NMOS, a PMOS and NMOS. For every NMOS, there's a PMOS. So um, I should have done this. All right. So let's, I know that's a terrible color, but this is just a reminder of the power in switching. Okay. And that these drains here need to be charged and discharged. All right. Now, in order to see some of the advantages and disadvantages, I have to introduce another concept called and or invert. And let's start with the NMOS stack first. All right. So if I want to discharge this, A and B have to be both on, right? But I can even get some logic kind of done very efficiently. See here, where now if A or B are both on, or C or D are both on, it'll discharge. All right. Now, that's great for the discharge, but how do we charge? Well, what was in parallel becomes in series, and what's in series becomes in parallel. So these are in series, they become parallel. All right. Okay. So now, in order, when you're designing one of these gates, you need to know its capacitance, right? So what you do is you assume like the worst case, so that if B is switching off and on, right? Well, A has to be high, and then if C is high, and then D is low, right? That means the current will only flow through here. Because if it could flow through both, it would be faster, right? But I have to count up the capacitances. So this is on. So this, this, and this all need to be charged and discharged. 1, 2, 3, 4, 5. Okay. Now these don't, because I'm not showing the body. The body is tied to ground. These sources are tied to ground, so they're shorted. Okay. Now, what about on the PMOS side? 1, 2, 3, 4, 5, 6. All right. So that's 6 drains or sources to be tied up. Now, there are layout tricks where you can share, like this actually shares a region, so it counts as half. But for this analysis, we'll just keep it. So you can see that in order to have the charge and discharge paths, you need, for every NMOS, you need a PMOS. And also that means that's an input, right? Where you have an input capacitance that you have to charge and discharge. So Um, which you might wonder, why am I doing that, right? Well, you're doing it for the power savings, and when it comes to automatic testing, these circuits are a lot easier to test. Oh, and also, that was and then to get it to work, you add an inverter. Okay, just for those of you wondering. But this is a very compact way to do circuits, right? You can do whole adder chains like this. So let's just, this whole thing would go, right? Because these other inputs are constant, I can switch this whole gate, right? And I'm just gonna look at that gate. And now let's just think of the current as being a lot more than what the inverter was. All right. Now we can talk about multi-logic, okay? So before, right, we have our regular two-valued logic, we have a high, and we have a low. However we do it, right? But multi-state, tri-state logic does this. So we have high, middle, and low. And this is not called middle, right? And it's helpful to realize that the slope here at these points is -1. That's what makes it a logic gate. That anything in here, there's actually a high gain, right? Because V out, the slope of this is the gain. And so if you have anything in here and a little bit of noise, it'll get multiplied one way or the other. But you have to pass through -1 twice to get 2. So over here, 1, 2, 3, 4. If you have -1, slope, -1, -1, -1, flat, 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 and even maybe not so flat, right? You have now 3 logic levels. And here's the issue. This is our V out equals V in line, kind of, right? So it's 1. And so logic level middle is right at the maximum power point. So you could say, well, half the time I'm high, a third of the time I'm high, a third of the time I'm low, a third of the time I might be here. So that means like 1/3 of the time I'm going to drop uh, this amount of current, right? And that current flows through everything, right? And I'm just saying it would look the same, except you'd have a symbol like Q for quantum device, right? So everything's the same. So it's I times VDD, where the other two states don't, all right? And then power, you could be going from here to here, here to here, or here to here, and that would have like a similar, you'd have to modify the other equation. So now the advantage of these, in this case, tri-state logic is, well, you can fit more data per line, right? So more data per line means less lines, means less off-chip communication, which reduces power. That's a lot of advantages for reducing power. But 1/3 of the time, on average, right, you're going to be here, burning a lot of power. Now, there's a way around that too. If we go to 4 states, okay, and now I'm just, 1, 2, 3, 4. Okay, I'm drawing that wrong. One, two, three, four. Now, this spot here is now in the, you're switching through. You don't stay there. You don't stay at the worst point. However, notice there is, I'll expand it a little bit. All right. There is current flow here and here. Okay, it's less, right? But so still we have this spot. So what we want to do is not be there. And what we can do is something called dynamic or domino logic. All right. And just very simply, I'm going to use the previous slide or previous. So I'm going to take that whole PMOS stack, okay, and replace it with one transistor. The NMOS stack remains, okay, because they're faster, so therefore you don't need as much width, so you can cut down on the area. A, B, C, D. Okay. And now what I'm going to do is I'm just going to, for an example, right, C is just going to normally be on. Okay. A, I'm just going to keep on. And then D, I'm going to turn it off. Now, to make sure that happens would take some logic, right? And what I'm not showing you here is you want to make sure things don't discharge when you want. So what you do when you don't want is you put a transistor here on the bottom. So when this goes on, or when this goes low, this charges, but then it makes sure that it can't dissipate. All right. But I just don't want to show that. I'm just trying to show that, B is going to control this. So what happens is you can have a clock or an enable, right? And when this is high, it's off, right? So nothing flows. And so we can call that evaluate, right? So let's call that Vx. So Vx will go from high to low, and all these capacitances have to discharge, all right? And that one too. But then when it goes low, this turns on, right? And again, I can have this footer make sure that this won't discharge, and then I'll charge everything up. I still have to charge all these capacitances, but it charges everything up. No matter what, during the pre-charge, I go high. So now I'm here. So what that means is if I had a 1, 2, 3, 4, right? If I'm here or here burning power, when the clock comes along and charges that node up, it puts me into a low power state. So I will be here for a certain amount of time to get the data out, right? But I can, by manipulating, and here, I'll just, if it's bothering you, right? Now, yeah, the footer adds some capacitance, but again, you've gotten rid of the whole stack, right? So here now, we have one drain capacitance, 1, 2, 3, 4, 1, 2, 3, 4, 5, 4, 1, 2, 6, 6. Not quite sure why I said 5 the other time. Anyway, but we only have one. And the thing is if we go back here, something failed to mention, is that to make the rise and the fall times equal, these PMOS, on average, have to be twice the width, which then they have twice that drain capacitance to discharge and charge. Okay. So just from a regular thing, that this logic style, right, reduces area, reduces these drain capacitances, which can reduce the power. Now, what you used to do is taking all that into consideration, you would just run everything faster, right? But if you're trying to squeeze more things on a chip or reduce the power, this can be helpful as well. The disadvantage is testing is harder. And when you charge this up, right, it will leak away at some point. Okay. So you can't really static test things. But the Atari 2600 used this technique to fit everything on a chip for that game console. So they just couldn't use static CMOS, right? So, but rather than taking things to the extreme in speed, they just were able to get the area down. All right. So yeah, this is a technique for regular CMOS that's just harder to test, and you can have testing costs drive things up. Uh, anyway, but now the advantage to using this domino or dynamic logic, right? And believe me, there's tricks to get things to kind of work, right? You can kind of have a feedback path that keeps that charged, right? This is just it at its simplest, right? But now I'm no longer staying here. I'm here while I read it out, right? So as soon as I switch to that level, I read it out, and then I go into this state. And then this, of course, stays low. So, if we look at it, right, what would a layout of even that look like? Let's see. How would I want to do that? So this is going to be the source and drain regions of this, right? And then I would put two polysilicons here, right? So that's A and B. And yeah, I can share a drain area. Then over here, right? right? A, B, C, D, and then, I just put an X, there's a contact here. And this is a physical wire, right? And I can draw the footer. And again, the body connection isn't shown, right? So you can see all those areas, right? Now, just to see, we can come back here, right? And what I can try to do is draw, oops, draw this PMOS stack, right? So these are in parallel, right? I'm going to draw them like twice as wide as the NMOS. Hopefully you can get an idea of it, right? And I'm switching it. I'm going up and down now. Okay. And again, there's layout tricks, right? That can be VDD, VDD. So the current can flow either way, right? And then it comes, I can just draw that here, here. And so this one, there's a end well around here, which is tied to VDD and it shorts it. So I have this area to charge and discharge, which is better to connect it this way than the other, the other way. Here it doesn't matter. Everything's got to charge and discharge. So you have an area here, an area here, another drain, and another drain. Okay. Where the this this direction is the width. So just think of it as smaller. So this whole thing, all this is then removed, right? So we're left with this. Yeah, we have some capacitance here. And we're no longer hanging out here or even here. So we can reduce the power. All right. So the thing about these, like with 4 devices, right, that would have been 2 lines. Now it's down to 1. So you're saving area. And the other thing about saving area is like, what you can, the chip size is, limited to a point, right? So the more you can pack in here, the less data you have to send off and on chip, which is saving power, right? So, well, NVIDIA is doing a great job in the AI space. Their GPUs do burn a lot of power, right? And so a research area is to come up with new architectures, new circuits, new materials to lower the power, right? With these models, you're kind of having reads and writes to memory, right? There's even like, well, can I have a memory right nearby, right? It's called compute in memory or content addressable memory. Anyway, that hopefully the sound was turned on this time. That's really, I think, a good summary of how multi-state logic using Domino can lower the power. But even Domino can lower the power in the area. Okay? I assume people are doing that. I guess a literature review would be good.